Okay. All right. Let me share my screen. Everyone can see this, right? Cool. So this is lesson one. This is basically like the first real lesson where we're going to start actually building stuff. And so it's basically just going to be introducing some of our discrete components, right? And when I say discrete, I mean basically like these, you can't really break down these components into anything simpler. Whereas like if we had like our integrated circuits, right, those are composed of like discrete components within them. So we're going to be talking about these, building some simple circuits, and then that will sort of lay the foundation for the rest of the class, where we're going to start building more complex circuits. So yeah. Okay, yeah. So the agenda for today is pretty simple. I'm going to spend the first part of it analyzing a few different circuits, and then I'm going to build them just to demo. And then after that, we'll just have the rest of the time until, I don't know, 12:15. I'll be here. You guys can build the circuits on your own. And then if you need help, you know, you could just, I don't know, we could set up breakout rooms or whatever. We'll figure it out. So yeah, that's pretty much the agenda. So this is kind of what the future looks like. This is what the final circuit looks like. Hopefully it's not too scary. There's kind of a lot going on here, but by the end of it, I think everyone should have a firm understanding of what's going on here. It's not as bad as it looks. There's a lot of stuff, but we're going to take it one step at a time. And so today we're just going to look at the fundamentals, right? Like, and we're going to slowly build until we get to here. So now what I want to do is talk about the first circuit, but I want to draw it on the whiteboard. So let me stop sharing. Let's see. All right. Can everyone see this? Fine.
It's a blank screen, right?
Yeah. Okay.
I can see it.
So the first circuit we're going to talk about is basically just like the hello world of circuits. Like, I don't know if anyone's here programs, but it's basically like the first introductory circuit, which is going to just be lighting up an LED on a breadboard. So it's a really simple circuit, but it'll help you understand, you know, how a breadboard works if you never used a breadboard, and how an LED works as well, in the sense of like, you know, because we have to choose like a specific resistor value, and we're going to do some like current calculations. So yeah, so before actually, you know, putting anything on a breadboard, we want to sort of derive some values and draw a circuit diagram, right? That's kind of what you want to do before you start just like putting components on a breadboard, because you don't want to, you know, accidentally short circuit something, or because once it gets more complex, it's not as easy. So right, so the goal of this circuit is to light up an LED. So how exactly do you do that? So let's see. Okay, this is working. Okay, so basically so an LED, I mean, looks kind of like this. The circuit component looks like on a schematic, it looks like this, right? And then like maybe that usually it has like some arrows just to show that it's an LED and not just a normal diode. But basically for an LED to turn on, which basically means current flows through it, and you know, it lights up, we need to have a certain voltage across its terminals called the forward voltage. So basically, if you don't put that minimum amount of voltage across the LEDs, then it's just not going to light up. So that's called the forward voltage. And this value sort of varies slightly based on the amount of current. So we need to sort of specify how much current we want to go through this LED. So the LEDs that I got for this, and usually it's pretty much the same for most LEDs, but depending on the color. But in this case, it's about 20 milliamps for a forward voltage of 2.1 volts. So, you know, in general, it's a good idea to refer to the data sheet, but for the most part, for most red LEDs, that's about the value. So like 20 milliamps and 2.1 volts. So you need 2.1 volts across the terminals, at least 2.1 volts. And then we're just gonna, we want 20 milliamps, and that's gonna make it light up pretty brightly. So now let me draw out the circuit. So yeah, so the first thing I want to tell you though is that you can't just place the LED in the circuit, right? Because if you just place it with a battery, right, it's just going to burn out because it's a short. There's nothing limiting the current basically, other than like the breadboard, which is very, very little resistance. So we're just going to assume that's a short circuit, right? And so it's really easy to burn out LEDs. I've done it many times. So whenever you're assembling these circuits, like please be sure to double check your circuit so that you're not shorting anything, because if one of your LEDs burns out, then now you have 7. So yeah, so let's actually derive the resistor value that we want to put down so that we can get 20 milliamps. So let me use, okay. So in general, this is what our circuit's going to look like. This is going to be our battery, and I'm just going to call it VB for the battery voltage. And then we have our resistor, and then we have the LED. And then this point's basically just ground. I mean, you can specify it if you want. But yeah, so this is going to be called R. We're going to derive R. And then remember I told you the voltage drop across the LED is some forward voltage, right? In our case, it's 2.1, but I'm just going to derive it generically. And then we basically just have, current going through. So, pretty intuitive. It's just a simple series circuit, right? We have basically two components here, the LED and the resistor. So let's just write, the simple, like using Ohm's law, right? So we know that this point is VF, right? Because this is ground. So what we can say is VB minus VF, right, over, right, this resistance equals the current, right? Pretty simple stuff. So now what we want to do is, right, we want to derive this resistor value. So we can just rearrange this to say R equals VB minus VF over I. And we specified that we want I to be 20 milliamps. So now let's just, plug in our numbers and see what we get. So R equals, and we have a 9-volt battery, so 9 volts minus, and our VF is around 2.1 volts, and then I is 20 milliamps. So we need to make sure this is in amps so we get the right number. So 20 times 10 to the negative third amps. And if you put this in a calculator, what you're going to get is 345 ohms, right? So if you looked at the parts list, you'll notice we don't have 345 ohms, we have 330 ohms. That's because 345 ohms is not like a standard resistor value. So we just go to the next best thing, which is 330. So we're not actually going to get 20 milliamps, we're going to get a little bit more because our resistor is a little smaller. So yeah, so this is basically, oh, people are typing in the chat. Oh, yeah. I don't know. I think I forgot to say that. Yeah. The forward voltage of this LED is 2.1. And yeah, you can just look at like data sheets to check it. But for most red LEDs, right, like if you just buy like some like giant pack of LEDs, sometimes they don't come with data sheets. So at least for most red LEDs, the forward voltage is around 2 volts. So we're just going to assume in this case that, right, the voltage drop is 2.1, and that we're, you can have less than 20 milliamps and it'll still be bright. It's usually like around 10 to 20 with like a maximum of 30 before you start, damaging it. So yeah. So now let me stop. Let me save this actually. Okay. Let me stop sharing so I can actually build the circuit on the breadboard and show you guys. Let's see. Okay. I wonder how this is gonna work. Oh, actually, what I can do is share my screen again. So the circuit, okay, yeah. So first let me just talk about a breadboard if you haven't used a breadboard before. So this is what it looks like. You have basically these power rails which go up and down, and then these sort of horizontal rails. So these power rails are like everywhere on one side is connected. So like, I don't know if you can see my mouse, but everything on this left side is connected, and then everything on this right side is connected. And it doesn't really matter which one you use, but you should use the left one for positive and the right one for negative, right? For power and ground. But it doesn't really matter, but it's good to just so you don't confuse yourself. And then these horizontal ones are all linked. So anything on this line is connected, anything on this line is connected, but these two are not connected, right? And so that's pretty much it. That's pretty much how a breadboard works. And so this is how our first circuit's going to work. So sometimes assembling a circuit on a breadboard can be a bit trickier than looking at the schematic, just because like in a circuit schematic you can connect multiple things at one node, but on a breadboard you have to do it all on the same rail. Like this is all the same like node. So this is basically just the circuit we just built, right? So that's the 330 ohm resistor, and then the LED. Oh, I forgot to mention one thing actually. LEDs are polarized, so they only let current flow in one direction. So you can't really see it here, but there's one leg that is longer, and that's called the I don't remember if it's the cathode or the anode. I think it's the anode, which is the positive side, and the cathode is the negative side. So you want the side that's going to be where the current's flowing through to be the longer leg, right? That's the positive side. If you connect it in reverse, it's not going to turn on. So let me. Then I'll share my screen. Okay, so I can turn this camera on. Okay. Stop share. Okay. So I don't know if you can see that well, but basically I have these two battery wires connected to these power and ground rails. And then I essentially just have, it's basically just I hooked up the circuit how I showed in the diagram. So I just have the resistor going from, I mean, it doesn't exactly matter where if the resistor is before or after the LED, but in this case, I just put it before. So it's going from the positive to this rail over here, and then the LED's positive leg, and then to ground. So if let me take this out. So you can see one leg is kind of longer than the other. So if I connect this in reverse, it's not going to light up. At least I don't think it will. Hopefully this doesn't damage it. Yeah, so it doesn't light up. Then if I reverse it, right, then it lights up. So it only lets current flow in one direction. So that's pretty much it for the first circuit. So yeah, are there any questions there? Hopefully that was pretty intuitive. Like, like you can message me privately too if you're uncomfortable. Okay, I'm just gonna assume that everyone got that. So that's basically just the first circuit. So if you have never built anything on a breadboard, that will be good practice. And also, just if you're working with LEDs, that shows you how to calculate the resistor value. So let's see. Next, I'm going to, let me go back to my whiteboard. Clear this. Okay. So now I'm going to introduce a new component, right? So we just talked about an LED and resistor. Now I'm going to talk about something called a potentiometer, which is basically it's another component that's going to give us a way to interact with our circuit, like while it's working. So potentiometer is basically just like, wait, this isn't working. Oh, it's basically just like a knob. And so what it looks like is kind of like this. Like if you look at like the inside of it. And so then you have this guy here, which is like a little wiper, right? And so basically you have these three terminals, right? So potentiometer has three terminals. And then over here, what you're going to have is sort of like this resistive material, right? That goes all the way across here. This is kind of a bad drawing. I'll show a picture of it in the notes. But basically, you have control over where this wiper goes. And so based on where the wiper goes, you know, there's going to be different resistance and then different current. But there's sort of two ways to set up a potentiometer. You can use it as a variable resistor, which is what we're going to use it for in our project, or you can use it as a voltage divider, which I'm not going to really talk about because we're not going to be using it like that. And it's, I don't know, it's just not really important for this project. But yeah, so if you want to use it as a variable resistor, all you really need are this terminal and this terminal, and you can just ignore this guy. So basically what happens is, let's say I have like, you know, my voltage source like this. So basically, you know, you're going to have, you know, current coming here. And then based on however much you turn this wiper, you're going to have some certain amount of resistance. So the more you turn it this way, right, the more resistive material there's going to be. So the bigger resistance there's going to be, and then, right, less current. But if I turn it all the way here, right, it's going to be very little current. So typically what you want to do is put a resistor in series with a potentiometer so that if you turn it all the way, you know, you don't just short circuit and, you know, kill your components. So now we're actually going to, let me derive a circuit, another circuit. So what did I want to draw? Oh, okay. So yeah. Is this making sense? Anyone have any questions? I'll assume that's no. Okay. So, right, we have our battery again. And then I said we want to connect a resistor in series. So this is going to be our 330 ohm. I'm just going to call it R1 for now. And then a potentiometer usually looks like this in a diagram. And then RP is going to be the maximum resistance, because you remember, like, it can be variable. You can turn it all the way to one side or all the way to the other side. So the actual resistance of this is going to be some fraction of it. So I'm just going to call it XRP, where X is some number between 0 and 1. Right? So it could be like, if you turn it halfway, the X is going to be 0.5 and you're going to get half the resistance. Right? And then we just have our LED. So I just added one more component into our circuit. And this is still VF. This is still I. So let me move this. So like I was saying, RP is the max, right? And then XRP is basically what it actually is. Did you mean to put the LED on the arrow leg of VR? What do you mean? What is VR?
Isn't the arrow leg on the variable resistor the center tap?
Oh, I see what you're saying. I see what you're saying. Yeah. So when you draw in a circuit diagram, this is how you this is just the simple way of drawing it. So here I only show 2 terminals, right? I would just assume we're not using the third terminal. So just assume this is like the edge terminal and this is the middle terminal. Yeah, sorry if that was confusing. So yeah, just pretend that like that's kind of what's going on. So we're just assuming the third terminal doesn't exist because we're not using it. So does that answer your question? Okay, cool. So okay, so these 2 resistors are in series, so we can just write this whole thing is basically just one equivalent resistor. So let's just basically write the equation we did last time, right? VB minus VF over, and in this case, right, we have 2 resistors, so R1 plus, and we're going to say XRP because we don't really know how far the potentiometer is turned, and then that equals I, right? So I can rearrange this and say VB minus VF. Hopefully my handwriting is not too bad. Over I equals R1 plus XRP. Okay, and then now I'm just gonna say, let's just solve for X to see how far we need to turn it so that I is 20 milliamps still. So if I basically solve for X in this, I'm gonna get VB minus VF over, let's see, IRP minus R1 over RP. Okay, so if I just plug in these numbers, let's see, 9 minus 2.1, and then we assume this is going to be 20 milliamps, so right, and then RP is the max, so our potentiometers are 500 kilo ohms, and then minus R1 is still 330, and then 500K. So this is actually going to be like a really small number. It's going to be, let's see, I did the calculation, 0.3 times 10 to the negative 4. So that's basically the fraction of how far you have to turn it. So you're saying like, okay, like what does this number even mean? So let me sort of make this more intuitive. So if you remember, because we're using a 330 ohm, it's actually more than 20 milliamps is going to flow. But if I force 20 milliamps, but I said here that 20 milliamps is going to flow, right? So if I do 0.3 times 10 to the negative 4 times 500K, that equals actually 15 ohms, right? That should make sense because in the first case, when we solved for 20 milliamps, we said, oh, 345 ohms, right? But we used the 330 ohm, right? So 330 ohm plus 15 ohm, oh, that's the 345 that we solved for in the beginning. So hopefully that kind of shows you like why we need to turn it this, we basically turn it so that this is 15 ohms, right? And then this is 330, right? So then we basically get the 345 that we solved for in the beginning. So yeah, so I guess that's kind of neat. So yeah, are there any questions there? It's kind of like a lot of writing here, but okay, let's see. Can you practically turn the wiper that little? No, yeah, basically not. Honestly, if you, it's probably more than 15 ohms when you turn it all the way in one direction because it's, Like it's not exactly 0. Like if you measure the resistance by just turning it all the way in one direction, it's probably more than 50 ohms. But this is just like an example to show you, I guess, you know, how a potentiometer works. But yeah, so let me show you what the actual circuit looks like now. So save this. Yeah. Okay, so let's see.
I'm having a hard time trying to turn the potentiometer.
Yeah, these aren't the greatest potentiometers. If you have like a flathead or something, it'll be easier to turn. But yeah, sorry about that. So let's see. Let me share my screen to the slides again. Yeah, so that was the first circuit. This is basically the second circuit. So you can see here, nothing is connect. Oh wait, no, this is the wrong one. This is the right one. So you can see here, there's nothing connected to this third terminal. We're only using the first 2 terminals. So basically, right, just what we just showed. You have the resistor to the potentiometer. So basically 2 resistors, and then the LED, and then back to ground. Okay, so it didn't look like building the circuit live really helped because you can't really see it. So I'm just not going to do that. I'll share these slides with you guys like right after I finish talking about the third circuit, so that you know, you can look at how to build it. So yeah, so that's the second circuit. I'm just going to skip this third circuit. This is the using a potentiometer as a voltage divider. It's not really important because we're not going to be using it for that way. So yeah, so the third circuit is going to be talking about capacitors. So okay, but did everyone get like the reason we're using a potentiometer here? Just basically just changing the amount of current that can flow based on how far you turn it, because you're changing the resistance. So okay, yeah, a capacitor. So personally, for me, capacitors were not super easy to understand the first time I was using them. So they can be a little bit tricky, but basically it's just a storage element that can store electric charge, kind of like a battery. So I don't know if anyone actually read through the stuff I sent or watched like the video, but it gives some nice visuals. But basically, when you place like a capacitor in a circuit, it basically starts charging up until it matches whatever voltage you're putting across its terminals. So yeah, it's kind of like a tiny battery, but it charges and discharges much more quickly. So I guess one important thing to mention is that capacitors don't follow Ohm's law, just like a resistor. So they're actually have a non-linear relationship with the like their current voltage relationship is not linear. It has to do with time. So what time is it right now? 11:30. Okay. So I was gonna just show you how to solve the differential equation to get it, but I guess that's gonna take up way too much time. So instead I'll just show you how to build the circuit, and I'll just post the notes after. But yeah, so a cool little circuit you can build with a capacitor is basically if you want your like LED to sort of fade. So what you can do is, let me switch screens. So if you had like a circuit like this, this is what a capacitor component looks like in your circuit, and then like your LED, right? So basically what happened in this circuit is, you know, current starts flowing, this capacitor starts charging up, and at the same time the LED is on. So what you can do is if like you were to like this, so let's say, you know, you turn, so this capacitor is going to charge super quickly depending on the value. So our capacitors are pretty small. I think it's like we have one that's 0.1 microfarad and one that's 10 microfarads and one that's 0.01 microfarad. So that's really small. So basically what's going to happen is this is going to charge like super, super quickly. And I just put a resistor here so we're not just like, it won't draw a huge amount of current. So basically what's going to happen is this capacitor is going to charge up to VB after some amount of time, right? And then and then once it charges up, let's say I just disconnect these terminals, what's going to happen is, right, now what's going to happen is it's going to discharge and then light up our LED for a small amount of time. So the problem that we have is that our capacitor is really small. And so in the case of just a simple series, what's called the RC circuit, right? There's something called the time constant, which is basically how long it takes for the capacitor to discharge to like around like 63% of its voltage. So that's R, basically it's R times C. So if we make our like, so our capacitor is really small, right? 10 microfarads. So that's like 10 times 10 to the negative 6, right? And this is in seconds. So if we want to make this seconds, we need a huge resistor value, right? But the problem is if we make a resistor huge, our LED is not going to light up because it's going to be way too little current to actually make it light up. So what we can do instead is boost the current using something called a BJT. So I'm not going to really go into the details right now. I'll go into it in another lesson. But a BJT is it's a bipolar junction transistor. It's basically it's a transistor. So I don't want to like go into the details because you could talk all day about this. But basically what our circuit's going to look like is this. Let me see how I drew it. Basically like this. So this guy right here is the BJT. So basically what's going to happen is, oh wait, I forgot the capacitor. So basically what's going to happen here is, let me explain really quick what a BJT does in this case. So BJT has 3 terminals, the base, the collector, and the emitter. So basically what happens is, what a BJT does is based on how much current comes into the base, it amplifies that based on how much current comes down here, based on this relationship. So, this should be IC. So basically the amount of current that comes down here is some beta value times however much current comes here. So basically just going to amplify it. So in our case, what we want to do, right, since our capacitor is really small, we don't want, if we discharge a lot of current, right, it's going to discharge in like 0.001 seconds, right? It's going to be super fast. We want to discharge a very small amount of current, and that can just be amplified by this BJT. So finding the time constant for this is not really trivial. It has to do with like the input resistance of this BJT. So I'm not gonna, maybe I'll post the notes after. But yeah, so basically what's gonna happen is this capacitor is gonna charge up and it's gonna discharge really slowly because, you know, this input resistance is pretty big. And then what's gonna happen is basically the current's gonna get amplified so the LED can still light up. So we still have enough current to light up this LED. And so the LED is gonna sort of get dim really slowly. And the voltage of the capacitor is kind of gonna look like this, right? It's gonna slowly decay down to 0. So I know that was like really quick. So if you have any questions, I mean, I'll post more detailed notes, but if you have any questions, you know, feel free to ask. Let me show you the actual circuit. So this is what the circuit looks like. It's kind of harder to see it on a breadboard, but basically what we're gonna have is this this 9 volts is gonna come down here. It's gonna basically like turn on the BJT in a sense, but at the same time, it's also gonna be charging this capacitor. So, oh, I think someone wrote something in the chat. Yeah, the beta value is sort of for the transistors we're using, it's around 300, but yeah, it's slightly different based on, you can look at the data sheet for this, but for our transistors, it's 300, and I just measured it using the multimeter just to double check. So yeah, our beta value is going to be 300. So basically what's going to happen is this capacitor here is going to charge up. Oh, another thing to mention, if you use an electrolytic capacitor, it's probably going to be polarized, right? Which means one, just like the LED, right? You want the positive side to be where the high voltage is and the negative side to be where the lower voltage is. So the stripe, I don't know if you can see the stripe here, that's basically the negative side. So what's going to happen is we're going to have current, right? It's going to be limited by this resistor, and it's going to charge up this capacitor, but at the same time, it's going to go to the base, which is this middle pin of the BJT. And then we also have 9 volts here at the top. And so what's going to happen is this small current is going to get amplified and then come to this LED and then light it up. And so then once I pull this resistor out, that's basically going to take it's going to disconnect the battery from this part of the circuit. It's still going to be connected here. But then what's going to happen is the capacitor now acts as your like mini battery, I guess you could say. And it's going to discharge slowly, and then basically this LED is going to fade. So I already have this circuit built. So let me just turn the camera on again. So let's see. Yeah, you when in doubt, just always look at the data sheet. So let me switch camera. So this is what the circuit looks like. It's kind of hard to see because of the LED. But basically, I have the BJT there, I have the resistor and the capacitor. So once I, this is kind of hard to see. Okay. So I'm just gonna, okay, let me do it like this. So once I remove this LED, what's gonna happen is the voltage, this battery is gonna be disconnected from the base. So what's gonna happen is the capacitor is gonna discharge. And so I'm gonna pull this out, and you'll see the LED slowly fades away, right? And it's kind of hard to see, but it's still on because the capacitor is still barely discharging, because it never really, it sort of like gets to zero as time goes to infinity. So if I plug this back in, it's gonna light up, and then if I remove it, slowly discharges away. So yeah, so those are the 3 circuits I wanted to talk about. But that wasn't too fast. Let me share the slides with you guys in the link. Share. Okay, so I'm gonna send the link in the chat, and now you guys can just look at the circuits and then basically just build them. Tell me if you guys can access this link. Hopefully it's not like telling you need permission or something. And then I don't know if you guys want to do like breakout rooms or something. Okay, cool, link works. So I'm gonna stop recording now.